engineering, we are going to talk about linear systems. In the last lecture, we obtained error bounds for elementary operations such as addition, subtraction, multiplication, and division. Before starting our discussion on linear operators, which are typically written as A times X is equal to Y, we would like to spend some time on error analysis of functions in general. In particular, we would like to bound the error in a dependent variable y, a function of independent variables x1, x2 up to xn, in case the errors in the independent variables are known. For instance, if our function is a linear function, if we know the errors in the independent variables ax, x, then we want to find out what would be the error in y after we operate on x with the linear operator a. We would also like to talk briefly about a type of numerical operation that is particularly prone to errors and that often leads to problems in the solution of linear systems. Numerical calculations involving subtractions between two numbers, where the difference between the operands is considerably less than either of the operands, are prone to large errors. Suppose we wish to calculate y is equal to x1 minus x2, and the error in the calculation of x1 and x2 can be denoted by delta x1 and delta x2. That is, x1 and x2 are my independent variables, and I know the error in x1 and x2, which is given by delta x1 and delta x2. Then the error in y, delta y, is given as bound on the error in delta y, mod of delta y is lesser than or equal to mod of delta x1 plus mod of delta x2. We have seen this from our last lecture where we found the bounds on operations, simple operations like subtraction. So, from that equation, dividing both sides by mod of y, we get delta y by y mod of that is lesser than or equal to mod of delta x1 plus mod of delta x2 divided by mod of delta x1 minus x2. It is clear from the last expression that the relative error in y will be very large if mod of x1 minus x2 is small, that is, the two numbers x1 and x2 are nearly equal. For example, if x1 is equal to 0.5764 and the absolute error in x1, that is delta x1, is 0.5 into 10 to the power minus 4, and x2 is equal to 0.5763 and the absolute error in x1 is in x2 is also 0.5 into 10 to the power minus 4. Then x1 minus x2 is equal to 0.0001, but the error bound on the numerical approximation of x1 minus x2 is the sum of the absolute errors in x1 and x2. So, that is equal to 0.5 into 10 to the power minus 4 plus 0.5 into 10 to the power minus 4 equal to 0.001. Thus, the error bound on x1 minus x2 is as large as x1 minus x2. Recall, x1 minus x2 is 0.0001, but the error bound is actually 0.001, which is actually an order of magnitude greater than x1 minus x2. Hence, the error bound is as large as the estimate of the result. One can avoid errors due to cancellation of terms by rewriting formulas to avoid subtraction between nearly equal terms. Let us consider in general a function y which is a general function of x1, x2, x3 up to xn, and let us suppose we want to estimate a bound for the magnitude of the error. That is, we want to find out a bound on delta y where y is actually a function of x1 tilde, x2 tilde up to xn tilde minus y of x1 0, x2 0 up to xn, where x1 tilde, x2 tilde, xn tilde are the approximate values for the variables, while x1, x2, x10, x20, xn0 are the exact values of the variables. So, the variables are x1, x2, xm whose exact values are x10, x20 and xn0, and x1 tilde, x2 tilde, xn tilde are the approximate values for those variables. We want to find, given that we have the approximate values of x1 through xn, which is x1 tilde through xn tilde, we want to find what would be the error in y due to the error in x. This general problem is of great interest while performing experiments where empirical data are put into mathematical models. For instance, we do some experiments where we find the values of x1, where the independent variables in my experiments are x1 through xm. I do that experiment and I find the values x1 tilde, x2 tilde, xn tilde. Because of some experimental errors, x1 tilde, x2 tilde, xn tilde are not the exact values which are actually x10, x20 and xn0. But given x1 tilde, x2 tilde and xn up to xn tilde, I want to find what is the error in y due to the error in my experiment, but due to my experimental error. So, we denote x tilde is equal to x1 tilde, x2 tilde through xn tilde, and x0 is equal to x10, x20 through xn0, and we denote delta xi is equal to x1 tilde minus xi0, and delta y is equal to y of x tilde minus y of x0. That is the numerical solution, which is y of x tilde minus the exact solution y of x0, which gives me my error in y. It can be shown that delta y is approximately equal to the sum of the partial derivatives of y with respect to the independent variables xi evaluated at the approximate solution x tilde times delta xi. Since that is true, the bound on y must be lesser than or equal to the sum of the individual partial derivatives times the error in each of the individual variables. That is, mod of delta y is lesser than or equal to sigma I is equal to 1 to n mod of del y del xi evaluated at x tilde times mod of delta xi. This result again we get from our previous lecture, where we talked about the error bounds on sums. One can derive the previous formula, this formula, as follows. Suppose we go from x0 to x tilde, x0 being the exact solution, x tilde being the approximate solution in n steps. In each step we start with x0, x10, x20, x30 up to xn0. At each step we change one of the individual variables to its approximate value. For instance, when we go from step I minus 1 to step I, we change xi0 to xi tilde. Otherwise, all the variables, all the independent variables have the same value between xi minus 1 and xi. It is only the independent variable xi which changes value from xy0 to xi tilde. Obviously, if we perform this through n steps, at each step changing the value of one particular independent variable, at the end of the n steps our xn will be equal to our approximate solution x tilde. In going from the I minus 1th step to the ith step, the ith coordinate is changed from xi 0 to xi tilde, while the rest of the coordinates are left unchanged. Because of this, due to the mean value theorem, there exists a xi I which belongs to the interval xi minus 1 xi, such that y of xi minus y of xi minus 1 is equal to del y del xi evaluated at xi I times the interval, which is equal to xi tilde minus xi 0, which is approximately equal to del y del xi evaluated at x tilde dotted with delta xi. The approximation is because we have evaluated the partial derivative of y with respect to xi at xi by the partial derivative at the end of my n steps. That is, I am evaluating del y del xi at the final value, which is x tilde. Since delta y is equal to y of xn minus y of x 0, recall y of x 0 is the solution where with the exact values for the independent variables, and y of xn is the solution where we have replaced the independent variables, the exact values of the independent variables with the approximate values. So, delta y is equal to y of xn minus y of x 0. We can actually write delta y as the sum over I to n y of xi minus y of xi minus 1. It turns out that if we do this sign, if we do this summation, all the intermediate quantities are going to cancel out, and we would be left with y of xn with I equal to n minus y of x 0 where I is equal to 1. Because of this, we can rewrite this expression as delta y is approximately equal to summation. Basically, we are taking the sum. If we take the sum on both sides of this expression, then we get delta y from this expression. Delta y is approximately equal to sigma I equal to 1 to n del y del xi x tilde dotted with delta xi, which again from our bounds on the additions is equal to lesser than or equal to sum of sigma I equal to 1 to n mod of delta y del xi x tilde dotted with mod of delta xi. In the above, if we go back to our previous equation and look, we are actually approximating delta y by the total differential of y. This means that in a small neighborhood of x tilde containing x 0, we are actually approximating y with a linear function. Because however, because of the approximation involved in evaluating the partial derivatives of at x tilde, recall that instead of evaluating the partial derivatives at xi, we are evaluating the partial derivative at x tilde. There is some approximation involved there. So, what is actually done is that although we evaluate del y del xi mod of del y del xi at x tilde, 5 to 10% of the value is added as a margin of safety, because we are not evaluating del y del xi at the exact point xi I, but at x tilde, which is the approximate value. In order to get a strict bound of y of x tilde, one should use the maximum absolute values of the partial derivatives in a neighborhood of x tilde that includes x 0. This becomes particularly important if the derivatives have relatively large variation in the neighborhood of x tilde or the delta xi are very large. So, we are saying that in order to get a strict bound, we should not really evaluate the partial derivatives at x tilde, we should actually look for the maximum value of the partial derivatives in a neighborhood of x tilde that includes the true solution x 0. This is important particularly when the derivatives are varying significantly, there is significant variation in the derivatives. So, it is important that in order to obtain a proper upper bound, that we take the maximum value of the partial derivative in a neighborhood of x tilde. The bound for mod of delta y obtained above covers the worst possible cases where the sources of error delta xi contribute with the same sign and cancellation of error contributions is not accounted for. For this reason, the bound for mod of delta y thus obtained is called the maximal error. But the maximal error bound is often not very useful, particularly for a large number of variables, because it is too coarse. It predicts an unrealistically high error estimate. So, instead of using the maximal error, sometimes we use something which is known as the standard error. How do we get the standard error? We use the theory of probability to obtain the standard error. What do? We assume that the xi's are independent random variables with mean 0 and standard deviation epsilon I. If we assume that, it can be shown that the standard deviation in the dependent variable y is given by a summation of the partial derivatives of y with respect to xi square times the standard deviation square and the square root of that. That is epsilon, which is my standard deviation in y, and this standard deviation is known as the standard error. It often gives a more realistic estimate of the true error than the maximal error, because it gives a narrower bound. It gives a narrower bound. If instead of the previous error bound, this error bound is much more realistic. So, with that discussion, we are ready to talk about linear systems. Why are linear systems important? Because linear operators are basically the simplest type of mathematical operators encountered in numerical analysis. Even problems that are nonlinear often require us to obtain solutions of linear systems. For instance, if A is a square matrix, in many physical applications A is not always full and may have a special structure. Recall our definition of linear systems which we obtained earlier, which says that we want to solve the system Ax equal to y. Typically in those systems, in those linear systems, A is a square matrix, but in many physical applications A is not always full and may have a special structure. We will first explore some commonly encountered square matrices with special structures. We will first talk about triangular matrices. Triangular matrices have the following form. For instance, we have some matrices known as lower triangular matrices, which contain only non-zero terms below or at the diagonal. Either the terms are non-zero below the diagonal or along the diagonal. All terms above the diagonal are 0. That is a lower triangular matrix. An upper triangular matrix is a matrix which contains zeros along the diagonal, which contains zeros and all terms which are below the diagonal, which contain non-zero terms along the diagonal and above the diagonal. That is an upper triangular matrix. But both upper and lower triangular matrix share a common property, which is that the determinant of such matrices are given by the products of their diagonal terms. So, for the lower triangular matrix, the determinant of L is equal to L11 times L22 times Ln. Similarly, for the upper triangular matrix, the determinant of R is given by R11 times R22 times Rnn. Next, the other type of typical matrix that we are going to encounter in the solution of linear systems are partitioned matrices. It is often desirable to partition a matrix into blocks of sub-matrices. In general, any matrix can be thought of as being built of matrices of lower order. For instance, if A is a partitioned matrix comprising of A11, A12 through A1n, A21, A22 through A2n, AN1, AN2 through ANn. So, these A11, A12, A1n, these are all actually matrices, but they are partitions of the bigger matrix A. So, A11, A12 are all matrices of size smaller than the full matrix A. Operations on partitions. Addition and subtraction on partitions can be performed as if the blocks were scalars. That is, if Cij is the summation of two partitioned matrices A and B, then Cij is basically the sum of the partitions Aij plus Bij, Aij and Bij being blocks of the partition matrix A and B. So, basically let me go over that again. If A and B are partition matrices with blocks Aij and Bij, then if we want to sum those matrices A and B to obtain a third matrix C, then the blocks of C, Cij, are just the sum of the individual blocks Aij and Bij of A and B. If we want to evaluate the product C of two matrices A and B, where A and B are partition matrices, then we obtain the product by summing the products of blocks of A and B with the same row index and the same column index. That is, if Aik and Bkj are partitions of A and B, we obtain Cij, the partition a partition of C, by taking the product of Aik Bkj summing over k equal to 1 to n. So, by treating these individual blocks as if they are elements of a matrix, we can obtain the partition C of which is obtained we can obtain the partition C corresponding to the product of the partition matrices A and B. Next, we want to talk about block diagonal matrices. A block diagonal matrix is a matrix that can be written in partition form as A is equal to diagonal A11, A22 through Ann. That is, A is a partition matrix, but A11, A22, Ann are actually matrices. They are not individual terms in the matrix A. They may be full matrices, but they occupy diagonals on my full matrix A. On my matrix A, on the diagonals, instead of having individual terms, I have actually matrices. So, this type of matrix is known as a block diagonal matrix. It is as if the diagonal elements of A are actually blocks of matrices, blocks, partitions, right. Similarly, it is possible to define block triangular matrices which have the same structure as triangular matrices, but instead of individual entities on the diagonal or below the diagonal, we actually have blocks of matrices at these locations. For instance, L11, L21, L22 are actually blocks of matrices, but they have the same structure as a lower triangular matrix. Similarly, a block upper triangular matrix has the same structure as an upper triangular matrix. The only difference is these R11, R12, R1n instead of being individual scalars are actually individual matrices. However, when we try to evaluate the determinant of this block triangular matrix L, we can basically do the same, we can do the same thing that we did earlier. So, determinant of L is equal to L11 times L22 times Lnn, exactly like we did earlier. Similarly, determinant of R is equal to R11 times R22 through Rnn. So, the same structure follows, the same structure with individual upper triangular, lower triangular matrices had passes over, continues into block triangular matrices. Next, we want to talk about vector spaces. The set of all n dimensional vectors form a vector space Rn of dimension n. For instance, the set of all 3-dimensional vectors form a vector space R3 of dimension 3. Similarly, for 2 dimensions, the set of all 2-dimensional vectors form a vector space R2 of dimension 2. The inner product of two vectors x and y is calculated as follows. So, we define, this is how we are defining the inner product. We are saying that the inner product is defined by the product of the components summed together. So, the inner product of two vectors x y is equal to x1 y1 plus x2 y2 plus x3 y3 through xn yn. If x is considered to be a column vector, the inner product can be interpreted in matrix notation. The inner product between x and y can be interpreted in matrix notation as the transpose of x times y, as the product of the transpose of x and y. Next, we want to talk about the notion of linear independence. A vector y, which is obtained by taking a linear combination of vectors x1, x2 through xn by multiplying them with scalars c1 through cm, is said to be linearly independent if there is some set of constants c1, c2 through cn not all equal to 0, such that that sum c1 x1 plus c2 x2 through cn xn is equal to 0. On the other hand, the vectors x1, x2 through xn are said to be linearly independent when this condition is only satisfied if and only if all the c1 through cn are 0. So, x1 through xn are linearly dependent if there is some set of constants c1 through cn not all equal to 0, such that c1 x1 plus c2 x2 plus through cn xn is equal to 0. x1 through xn is linearly independent if that condition is only satisfied if all the c1 are 0. Basically, we are saying there is no set of non-zero constants c1 through cn such that we can sum x1, x2 through xn after multiplying them with the scalars c1 through cn such that we get 0. The maximum number of linearly independent vectors in Rn is n. Any set of linearly independent vectors x1 through xn form a basis for the vector space Rn. Any vector v belonging to Rn can be expressed as a linear combination of the basis vectors x1 through xm. That is, v, if x1 through xn comprise a basis for the space Rn, any vector v can be represented as a linear combination of x1 through xn. What do we mean by a linear combination? We can write v as a scalar multiple alpha 1 times x1 plus alpha 2 times x2 plus alpha 3 times x3 through alpha n times x n, where not all the alpha are equal to 0. Next, we want to talk about linear subspaces. The set of vectors given by all possible linear combinations of the vectors x1, x2 through xk with k less than n form a linear subspace R, and the vectors x1, x2 through xk are said to span the subspace R. The subspace R has dimension k if x1, x2 through xk are linearly independent. That is, the subspace R k has got basis vectors x1, x2 through xk. Next, we want to talk about the rank of a matrix. A rank of a matrix A is said to be R if R is the maximum number of linearly independent column vectors or row vectors of A. So, basically the rank is the maximum number of linearly independent column vectors or row vectors of A, and those the maximum number of linearly independent column vectors of A is always equal to the maximum number of independent row vectors of A. Rank of A therefore must be lesser than or equal to the smaller of m and n, where m is the number of rows in A and n is the number of columns in A. Since the number of linearly independent columns must be equal to the number of linearly independent rows, it is obvious that the rank, which is equal to the number of linearly independent rows and number of linearly independent columns, must be lesser than or equal to the minimum of m and n. If the rank is equal to m, that is, if m is equal to n means A is a square matrix, and if the rank is equal to m and equal to n, then the matrix A is said to be non-singular. That is, it has got a non-zero determinant, that is, it can be inverted, it is invertible. A linear system of equations with m equations and n unknowns, when we actually write it out, which we have not done up till now, can be written like this: A11, A12, A1n are the components of the coefficient matrix A, x1, x2 through xn are my independent variables x. I can think of x as a vector with of dimension n, and B is my right hand side, and we want to solve for x1, x2 through xn, which satisfies this condition Ax equal to B. If B is equal to 0, the system is said to be homogeneous. So, Ax is equal to 0 is said to be a homogeneous system. A homogeneous system always has a trivial solution. What do we mean by a trivial solution? That is, a homogeneous system will always be satisfied by x1, x2, x3 through xn equal to 0. If rank of A is equal to R is less than n, then Ax equal to 0 has n minus r independent solutions. Any vector x which satisfies Ax is equal to 0 is a null vector of A, and the set of all such vectors comprise the null space of A. The null space of A has dimension n minus r, because as we recall, we said that if rank of A is equal to r less than n, then Ax is equal to 0 has n minus r independent solutions. So, the null space of A has dimension n minus r. The system of equations Ax is equal to b can be written as x1 a1 plus x2 a2 through xn an equal to b. Basically, we are taking the rows of A and multiplying, scaling each row by x1 through xn, scaling the first row with x1, the second row with x2, the third row with x3, and so on and so forth, and the last row an by xn, and setting that equal to b. This is just another way of writing the system Ax equal to b. But this way of writing makes clear that b is actually a linear combination of the columns of A, which again makes it obvious that if the system Ax is equal to b is to have a solution, b must belong to the subspace R spanned by the columns of A, because recall that x1 a1 plus x2 a2 plus xn an is equal to b, which basically means that b is a linear combination of x1 x2 through xn. B is a linear combination of a1 a2 through an. x1 and x2 through xn are just the scalar multiples. So, b is a linear combination of the columns of A, a1, a2 through am. Thus, b must belong to the subspace R which is spanned by the columns of A. So, in this case columns of A are the basis of that subspace, and b is obtained by taking a linear combination of those basis vectors a1, a2 through an after scaling them with the scalars x1, x2 through xn. This condition can also be expressed by the requirement that rank of A B is equal to rank of A. What this means, since B is a linear combination of the columns of A, that means if we augment A by adding an additional column B, we do not change the rank of A, because B is a linear combination of the columns of A. So, if we add B, we add an additional column to A which is B, which does not change the number of linearly independent columns of A. So, since B is a linear combination of the columns of A, the augmented system has the same rank as A. If M is equal to N is equal to R, that is if A is a square matrix and has got full rank, then Ax equal to B has a solution for any vector B. Since now that A has full rank, the columns of A form a basis for the space Rn. A has full rank means A has rank n. That means each of the columns of A are linearly independent vectors, and since the space has dimension n, and since I have n linearly independent vectors which are the columns of A, which means that this implies that the columns of A form a basis for the space Rn, and since they form a basis for the space Rn, any vector B can be represented by a linear combination of the column vectors of A. Thus, any vector B can be solved for. Given any vector B, we can find x such that Ax is equal to B. Next, we wish to talk about eigenvalues and eigenvectors. Let Ax is equal to lambda x for a matrix of dimension m by n, a vector x and a scalar lambda. Then lambda is an eigenvector of A and lambda is an eigenvalue of A and x is an eigenvector of A. We can rewrite Ax is equal to lambda x as A minus lambda I, where I is the identity matrix, A minus lambda I operating on x is equal to 0. Notice that A minus lambda I x equal to 0 is a homogeneous system. From what we have looked at previously, this homogeneous system is only going to have a solution if determinant of A minus lambda I is equal to 0. If we expand this determinant out, if we write out the determinant A minus lambda I, we get a polynomial in lambda, and that polynomial in lambda is called the characteristic equation of A. And depending on the dimension of A, the dimension of the polynomial also varies. For instance, if A is a 3 by 3 matrix, the characteristic equation is a polynomial, is a cubic, is a polynomial of dimension 3. If A is a 4 by 4 matrix, the characteristic equation is a polynomial of dimension 4. And depending on the roots of the polynomial, we get the eigenvalues of A lambda 1, lambda 2, lambda n, which may be real or complex numbers. But if we count each root equal to the number of times equal to its multiplicity, we get n real or complex roots of that polynomial, which are the eigenvalues of A. Next, we want to talk about similarity transformations. Let C be a non-singular matrix, that is, C has determinant which is non-zero, that is, determinant of C is greater than 0. Then the transformation C inverse AC is said to be similar to A. That is, if we start with our original matrix A and when we transform it according to the rule C inverse AC, then the matrix we get C inverse AC is said to be similar to A, and the transformation is called a similarity transformation. Let us go back to the eigenvalue problem Ax is equal to lambda x, and suppose we perform a similarity transformation on A to get C inverse AC. We can see that if we pre-multiply both the left hand and right hand side with the matrix C inverse, we get C inverse x Ax is equal to lambda times C inverse of x. C inverse Ax I can rewrite as C inverse AC operating on C inverse times x, because C and C inverse on taking the product, they give me the identity matrix. So, I can rewrite Ax is equal to lambda x as C inverse AC operating on C inverse x, which is equal to lambda operating on C inverse x. But this equation, in this last equation, this has the exact structure of an eigenvalue problem, which becomes evident if we replace C inverse AC with B. Now, so that we can write B operating on C inverse x is equal to lambda times C inverse of x. Thus, we see that for after similarity transformation of A, the similar matrix C inverse AC has the same eigenvalues as A, it has the same eigenvalues lambda, but its eigenvectors are no longer x, they are now C inverse x. Thus, after similarity transformation, the eigenvalues are preserved while the eigenvectors are transformed as C inverse of x. An arbitrary square matrix of dimension n by n has n eigenvalues and n eigenvectors, each of which satisfy the relation Ax xi is equal to lambda xi. These n equations can be, if we can combine all these equations together, we can write it in matrix form as Ax is equal to lambda x, where now x is no longer a vector, x is a combination of all those eigenvectors. Each eigenvector occupies a column of the capital matrix X. So, x1, x2 through xm are individual eigenvectors, and I have combined them together to form the matrix big X, and lambda is another matrix which is basically a diagonal matrix, and the diagonal elements of lambda are the individual eigenvalues lambda 1, lambda 2 through lambda n, corresponding to the eigenvectors x1, x2 through xn. If the eigenvectors are linearly independent, x is going to have full rank and is going to be non-singular. Why? Because if the eigenvectors are linearly independent, each of the columns of A are linearly independent, and each of the columns of x are linearly independent, x has full rank, and thus x can be invertible and x is non-singular. Since x is invertible, we can write x inverse Ax is equal to lambda. Basically, we pre-multiply Ax is equal to lambda x with x inverse both on the left hand and the right hand side, when we get x inverse Ax is equal to lambda. And recall, lambda is a diagonal matrix, that is, it has got zeros everywhere, and lambda 1, lambda 2 through lambda n on the diagonals. Thus, a similarity transformation by X, the matrix of eigenvectors, recall that earlier the transformation that we looked this relationship, this is basically a similarity transformation on A, right. So, what we are saying is that if we do a similarity transformation on A using the matrix X, we get a diagonal matrix. We transform A into a diagonal matrix which has the eigenvalues of A as its diagonal terms. If the eigenvalues of A are distinct, that is, lambda I is not equal to lambda j for any I, ei or j, then the eigenvectors are always going to be linearly independent. So, if a matrix has got distinct eigenvalues, that each of its eigenvalues are different from each other, then the eigenvectors are also going to be linearly independent. And we know that for a real symmetric matrix, the eigenvectors corresponding to distinct eigenvalues, in addition to being linearly independent, they are also orthogonal. So, that is not really true for always, but it is only true for real symmetric matrices when the eigenvectors corresponding to distinct eigenvalues are mutually orthogonal. What it means? What does orthogonal mean? It means that if we take the dot product of two of those eigenvectors, xi dotted with xj, or in matrix notation xi transpose xj, we are going to get 0. Even if all the eigenvalues are not distinct, the eigenvectors of a symmetric matrix corresponding to the same eigenvalues can be chosen to be orthogonal. There are procedures for orthogonalization which we are going to talk about later in this course, but basically for a symmetric matrix corresponding to distinct eigenvalues corresponding to an eigenvalue, if there is more than one eigenvector, we can make those eigenvectors orthogonal to each other. We can define the eigenvectors so that the dot product of those eigenvectors is equal to 0. Thus, for every symmetric matrix, there is an orthogonal matrix X such that X transpose X is equal to I, that is, such that lambda is equal to X transpose Ax. Next, we want to see how the eigenvalues change if we perform certain simple operations on a matrix. For instance, we have an initial matrix A, and suppose we add the same constant scalar C to each of the diagonal terms of A. That is, we form the matrix A plus C I, where I being the identity matrix. In that case, what happens is that the eigenvalues of A just get shifted. That is, instead of the eigenvalues remaining as lambda, the eigenvalues become lambda plus C. So, adding a constant to the diagonal term just shifts the eigenvalue by a constant C. So, that is one property of eigenvalues. The second property we want to talk about is if we take the product of the same, if we take powers of a matrix. For instance, if we take a product of a matrix with itself, for instance A square x, I can write it as A product with Ax, but Ax I know I can write as lambda x. Thus, A operating on Ax I can write as A operating on lambda x, but we can, since lambda is a scalar, I can move it out, and so we have lambda times A lambda x is equal to lambda times Ax, but again Ax is again equal to lambda x. So, we are going to get lambda square x. Thus, a power, if we take a power of a matrix, if we take nth power of A, then the eigenvalue of the nth power of A is basically the eigenvalue of A raised to the nth power. So, the eigenvalue of A to the power n is equal to lambda to the power n. Because of this property, if P is a polynomial of the form A0 z to the power n plus A1 z to the power n minus 1 through Am, and instead of z, if we replace that by the matrix A, then we can see that PA is going to have eigenvalues P of lambda. Finally, for today's lecture, I want to briefly introduce something which is known as singular value decomposition. In our next lecture, we are going to talk in much greater detail about this, but I just want to introduce this. So, suppose A is an m by n matrix of rank R, then there will always be a m by m orthogonal matrix. Recall what is an orthogonal matrix? An orthogonal matrix is a matrix all of whose columns are orthogonal to each other. So, if I take the dot product of a column I with a dot product of another column j, I am going to get 0. So, what I am saying is that if we can always do a singular value decomposition of a matrix A into orthogonal matrices U and V and an R by R diagonal matrix D, such that I can represent A as a product of U, sigma and V transpose, where sigma is such that D occupies the diagonal elements of sigma. Thank you. We will continue with this discussion in our next lecture.